Section. Introduction. In the field of natural language processing, NLP, there's a rising trend towards methods that don't rely on tokenization, such as pixel-based text representations. These methods have proven to be effective in handling languages that haven't been seen before and are more resilient to noise attacks compared to models that use tokenization. Moreover, pixel-based methods can take advantage of visual similarities between characters and scripts, as they allow for parameter sharing across all inputs. This makes them a promising avenue for multilingual NLP. Previous pixel-based models have divided the rendered text into consecutive patches or used a sliding window, similar to speech processing. While these methods have the advantage of creating compact and transferable representations, they also result in a large input space because there's no unique way to represent lexical units. This means that pixel-based models could encounter a new set of image representations with every new sentence, leading to redundancy in the input space and hindering the development of contextual language representations. In this study, we question whether structuring the input, which would result in more frequent parameter updates through unique word representations, could help pixel-based models gain a deeper understanding of context and semantics. We propose rendering strategies that provide the model with a compressed input space. We show that enforcing a rendering strategy based on bigrams, two-character combinations, leads to a model that is both more capable and more data efficient. For instance, a model with 22 million parameters performs competitively with the original model that has 86 million parameters. When we increase the parameters back to 86 million, the performance gap to BERT, trained on the same data, narrows. Further analysis reveals that the added input structure results in a clear visual token frequency bias in the learned embedding space. This bias, also found in BERT, has been shown to degrade the quality of embedding spaces when word representations are influenced not only by semantic relations but also by the number of model updates. We demonstrate that frequent words have more context-specific representations than infrequent words, particularly in the upper layers. We also show that pixel models acquire a significant semantic understanding during pre-training, but their sentence representations are easily influenced by this frequency bias. We build on the general-purpose language encoder framework presented in Pixel, a text autoencoder that uses a masked reconstruction objective. Instead of patches from natural images of objects, the patches now contain images of text. To convert text to images of text, Pixel uses a rendering library to produce an image at the sequence level, which is then sliced into image patches of size 16 by 16 pixels. The sequence length maximum of 529 patches is roughly equivalent to the memory requirements of BERT, the closest benchmark for Pixel. Previously proposed approaches to rendering text as images render full sequences of text and segment into either consecutive patches or with a sliding window. These continuous strategies result in a significant number of uniquely valued patches, many of which may be observed only once during training. We compare 4 rendering strategies: the original unstructured, continuous, and 3 structured, words, mono, bigrams. To render words, we separate segments with additional whitespace so that new segments begin at the start of the next image patch. Bigrams, rendering 2 characters per image patch, is chosen to be widely applicable, without knowledge of word or morphemic segmentation. The choice of character bigrams is motivated by what generally fits within a 16 by 16 pixels image patch. Mono instead applies monospaced fonts where each character is a fixed width. Depending on font size, this may result in character bigram patches without breaks within characters, but this is not guaranteed. The main difference between bigrams and mono is that mono simply slides across the sentence, 2 characters at a time, yielding 2 ways to represent a word, whereas bigrams render the words and then pad with whitespace, ensuring unique inputs. The structured rendering strategies result in a greatly compressed input space as measured by the number of unique image patches processed by the model, but it comes at the cost of longer sequence lengths. While the rendering strategies we propose were not specifically designed for English, they may not equally generalize to other languages or scripts. Section Summary. The section discusses the use of tokenization-free methods in natural language processing, NLP, specifically pixel-based representations of text. These methods have shown to handle unseen languages and be more robust to noise attacks. The authors propose structured rendering strategies, such as bigrams, which lead to more frequent parameter updates and enable pixel-based models to develop a deeper understanding of context and semantics. These structured strategies result in a compressed input space but may have limitations in generalizing to other languages or scripts. Section: Model Scale Variance. Let's remember from our previous discussions that the continuous rendering method generates a significantly larger set of unique image patches compared to other techniques. This means that models have to learn to encode many nearly identical visual representations, which can be inefficient in terms of both parameters and training efficiency. So, we theorize that pixel models that work with fewer unique image patches can be scaled down without losing performance. While base models and larger ones are commonly used due to their strong performance, proven scaling laws allow for more experimentation and model development at a smaller scale. This is not only more eco-friendly but also encourages contributions from those with limited computational resources. With this in mind, we propose two smaller architectures that we will test across various tasks. Our base model architecture is directly adopted from VIT and Pixel, and we introduce two more compact variants, small and tiny. The configurations of these smaller models are based on the VIT variants. We found that shallow decoders as small as 2 layers can be sufficient for VIT maze, so we apply a scheme of having the number of decoder layers at every scale reduction. We pre-train small models with the proposed rendering strategies and then evaluate them on dependency parsing, UDP, with data from Universal Dependencies version 2.10 treebanks, and GLUE, to explore the model's capabilities at syntactic processing on the word level and semantic processing on the sentence level. We pre-train all models on the English Wikipedia and book corpus data for direct comparison with Pixel and BERT, which results in approximately 16.8 million training examples. We follow the suggested hyperparameters used for Pixel with the exception of batch size. The smaller architectures of small and tiny allow for larger batch sizes, which we double from 256 examples to 512 and 1024, respectively. We then have the number of pre-training steps accordingly from 1 million to 500,000 and 250,000 in order to train for the same number of epochs as Pixel, approximately 16 epochs, but varying slightly due to differing sequence lengths per rendering strategy. Pre-training base takes 8 days on 8 by 40 GB NVIDIA A100 GPUs, while in comparison, pre-training small takes less than 48 hours on the same setup, and tiny less than 24 hours. To fine-tune our models for classification tasks, we replace the decoder used for pre-training with a task-specific classification head. We find that the more compact architectures often benefit from a slightly higher learning rate. When fine-tuning on GLUE, the structure follows what was seen during pre-training for all rendering strategies. We find that the word structure slightly outperforms bigrams and mono on this word-level task. For GLUE, we see a large increase in performance when rendering with any structure and especially bigrams. We find that bigrams is the best performing structure on average, even slightly outperforming the 86M parameters Pixel, average UDP, 76.1, average GLUE, 74.1, with only 1/4 its model parameters. Next, we pre-train tiny and base model variants with bigrams rendering to evaluate performance at different model scales. Section Summary. The authors propose smaller model architectures, called small and tiny, which are based on the VIT variants. They hypothesize that these smaller models, operating over fewer unique image patches, can achieve comparable performance while being more environmentally friendly and accessible for those with limited computational resources. The experiments show that the bigrams rendering strategy outperforms other strategies, even outperforming the larger Pixel model with only 1/4 of its parameters on average. Section: Model Scaling. We're going to discuss model scaling and how different model scales compare when using a bigrams rendering strategy. We've found that the tiny configuration, despite having only 5.5 million parameters, performs well on word-level tasks. However, it falls behind the small and base configurations on sentence-level GLUE tasks. The small configuration strikes a good balance between scale and performance, performing nearly as well as base on GLUE tasks and even slightly outperforming it on UDP tasks. Base, on the other hand, narrows the performance gap with BERT on GLUE tasks. We've also noticed that the more compact the model size, the greater the benefit from structured rendering. We've tested this by comparing the performance of bigrams rendering with a continuous rendering strategy. We've also ensured that bigrams rendering doesn't negatively impact performance on multilingual sentence-level tasks across different scripts and morphologies by including results on TIE DIQA Gold P. Here again, small performs well considering its size. Next, we delve into how bigrams rendering changes the model compared to continuous. We found that a structured rendering strategy improves downstream performance, but we wanted to investigate whether this is due to fine-tuning with structure or if the model develops strategy-specific features during pre-training. We found that a mismatch between rendering strategies during pre-training and fine-tuning leads to lower downstream performance. This is particularly true when switching from bigrams to continuous. Interestingly, this doesn't align with our findings for UDP tasks, where continuous overcomes the change to words structured rendering. This suggests that UDP tasks are easier for pixel-based models than high-level glue tasks. We've also found that base bigrams outperforms pixel by 3.6 points on average on Masaka NER, a named entity recognition benchmark for 10 African languages. This highlights the potential of pixel-based models for modeling low-resource languages. We then turn our attention to how bigrams rendering enables better performance on semantic tasks. We found that the extent to which language models capture semantic information is partly determined by their ability to contextualize text. We've analyzed how capable base bigrams is at producing contextualized word representations using the words in context dataset. We found that the model generates representations of a target word from different contexts with a low cosine similarity compared to target words in similar contexts. This suggests that a pixel-based language model is capable of forming contextualized word representations, although not as fine-grained as seen for BERT. We've also investigated the isotropic nature of the model. We found that the word representations are not evenly distributed with respect to direction in the embedding space, but instead appear to be anisotropic. This geometric alignment leads to an overestimation of their similarity, which is not an expected property of an expressive word embedding space. We found that transformer-based language models can develop a representation bias driven by token frequency, where low-frequency tokens are clustered together in the embedding space, leading to anisotropy in the model. This bias leads to poor word contextualization because the learned vector positions of low-frequency words have not moved far from their random initialization. Thus, their embeddings are not sufficiently distinct from unrelated words with similarly low token frequency. Finally, we found that compressing the input space in the form of structured rendering allows the model to build more contextualized word representations through more frequent parameter updates. We've investigated this by sampling inputs that were seen during pre-training with high and low frequency. We found that for pixel, the distribution appears as mixtures with a larger distribution mass at higher values of cosine similarity from comparing high-frequency words to other high-frequency than when comparing low-frequency to other low-frequency. For base bigrams, the frequent words both in isolation and in context are less directionally aligned with each other compared to the infrequent. This is in line with the representation degeneration problem and more frequent updates leading to better contextualization. Section Summary. The section discusses the performance of different model scales using a bigrams rendering strategy. The tiny configuration performs well on word-level tasks but lags behind on sentence-level tasks compared to small and base models. The section also explores the impact of rendering strategies on downstream performance and shows that a structured rendering strategy leads to improved performance on semantic tasks. Additionally, the section analyzes the contextualization ability of the base bigrams model and investigates the isotropic nature of word representations in the embedding space. The findings suggest that compressing the input space through structured rendering allows the model to build more contextualized word representations. Section: Frequency bias and semantic modeling. Let's delve into the topic of frequency bias and semantic modeling. We've noticed that the continuous rendering method doesn't seem to degrade the representation as much. However, its performance on the glue benchmark, as discussed in the model scaling section, isn't as good. This could be because the pixel method is exposed to a wide variety of patches, but not frequently enough. This is due to the many ways similar inputs can be interpreted by the continuous method. Interestingly, when we tried to switch the rendering strategies in the pre-training versus fine-tuning section, from continuous to bigrams, the performance dropped. This suggests that the model has developed specific expectations and features for each strategy, which are not easily adaptable. The new rendering strategy for fine-tuning introduces patches that likely remain in the low-frequency domain, meaning they are poorly contextualized. We've also noticed a token frequency bias in BERT, a popular language model. We decided to explore the relationship between the frequency of visual tokens and the performance of semantic tasks. In BERT, words that appear frequently have the most context-specific representations. On the other hand, the context influences the representations of infrequent words more. We found that this also applies to the base bigrams model, as shown in the self-similarity figure and discussed in more detail in the measuring similarity appendix. We hypothesized that sentences that only differ in casing would result in different representations if lowercase is used more frequently. This shows how the frequency of observed tokens can impact semantic modeling, which aligns with the biases we've observed in BERT's embedding space. To test this, we used the Semantic Textual Similarity Benchmark, STSB, which is also part of the GLUE benchmark. We calculated the cosine similarity between sentence representations and compared it with the gold standard similarity scores. The results, shown in the STSB accuracy uncased figure, indicate that both continuous and bigrams rendering during pre-training can lead to meaningful semantic modeling capabilities. Interestingly, the performance boost from simply ensuring all words are lowercase is about the same as the boost from switching from pixel to base bigrams. This is similar to how frequent and infrequent tokens in BERT have different influences on their context. Given that base bigrams has similar representational characteristics to BERT, future research could aim to improve pixel-based models' semantic capabilities by applying the advancements found in tokenizer-based models. Recent studies on pixel-based language modeling have shown how visual language understanding can be achieved solely through pixels. They've also highlighted the importance of visual similarity in languages for cross-lingual transfer and demonstrated how combining text and image modalities allows a single encoder to perform multimodal tasks. By directly using bytes, we can further unify these modalities. Our work is closely related to previous studies on machine translation with pixel representations. We've built on the foundation laid by Pixel for general-purpose language encoding with pixel-based representations. We've made hypothesis-driven improvements without needing additional data or a larger model. However, it's possible that a model using continuous rendering could perform competitively if it's pre-trained on more data for a longer time. Our addition of a bigrams structure is similar to the optional but highly beneficial 4 grams in the character-based canine model. While transformer-based language models have surpassed character-level n-gram models, character-level features are still valuable. They're less sparse and more robust to misspellings than word n-grams, and they're particularly useful for languages with rich morphology. Previous studies have suggested that character-level models might be better suited for languages with complex morphology than subword-based models. However, designing a semantically capable model has proven challenging. We believe there's potential for future research on pixel-based language models to explore effective strategies for learning morphological patterns.